Hi, my name is Corrado Altomare. I'm a postdoctoral researcher from Universitat Politècnica de Catalunya in Barcelona, Spain. This work is a joint collaboration between my institution, Flanders Agricultural Research Institute from Belgium, Politecnico di Bari and the University of Salento from Italy, and is funded under the European Horizon 2020 program. We all know that climate change is leading to sea level rise, but also more frequent and severe storms worldwide. We experienced in the last decades several sea storms. For example, one of the last one is the Gloria storm that struck the Mediterranean coast of Spain and the southern coast of France, with several damages and even casualties. Therefore, urbanized coastal areas are now exposed to more severe hazard, and this actually is very important because coastal areas worldwide represent the majority of the urbanized area. So most of the world population lives on the coastal zone. The main reason of flooding and therefore even of casualties in coastal areas is related to wave overtopping. That is still the major cause for this flooding. So point is, we should upgrade the criteria that we use for the design of our coastal structure, also to consider the effect of these climate change scenarios. To do that, we start to look at what proposed in EurOtop manual, that is a very well-known and one of the most referenced, let's say, work in in overtopping worldwide. EurOtop proposed for the safety of people, of pedestrian on sea dike or behind sea dike, certain criteria. These criteria are based just on mean discharge, for which certain ranges are proposed depending also on the local wave height of the tow, but also criteria are based on the individual maximum overtopping volume. Point is, for example, that the individual maximum overtopping volume only identify one value as threshold criteria, and is not clear whether or not this value is related to specific characteristic of the overtopping, let's say, flow properties. That is what we want to characterize. So we start actually from the general idea that there is a high importance of overtopping flow characteristic of people's safety that has been investigated, but not very systematically and not very in detail. We can cite only a few studies that consider overtopping flow depth and velocities in order to estimate the hazard for the pedestrian. These studies bring two curves, like those shown in this slide, that are sort of stability curves for pedestrian. So we decide to carry out an experimental campaign. This experimental campaign, of course, is carried out just for a specific layout that characterizes the Catalan coast, and the results should be, in future, extended to other layouts. Our goal, therefore, is to analyze the overtopping flows that can lead to risk scenarios for people. To do that, we measure the overtopping discharges and volume for different return period, and we characterize the flow depth and velocities that are associated to the maximum individual overtopping event. We try to relate them to the instability curves proposed in literature. Our case study actually is the case of Premià de Mar. Premià de Mar is a coastal town 40 km north of Barcelona that is characterized by a specific, let's say, problem. We have a railroad and a railway and also a bike path that are basically on the seaside, are very exposed to sea storm during the winter season, especially now where in several stretches of this area nourishment is not performed anymore. So there is also a lack of this protection. So we model this layout in our physical model facility that is a wave flume, a small-scale wave flume called CMITO, just 17 meters long and 37 centimeters wide. We employed several resistive wave gauges to measure the wave transformation along the flume, but also acoustic wave gauges to measure the overtopping flow properties on the dike crest, together with high-speed cameras. the choice of the foreshore slope, the dike slope, and the crest width dimension are based on the local conditions, so on the bathymetric and topographic survey at Premià de Mar. We perform up to 420 tests, varying the return period, therefore wave height and wave period, but also water depth at the toe of the structure, promenade width, and phase seeding. Related to the instrumentation, I want to underline how we used a sort of redundant system to measure the overtopping flows on the top of the dike, that consists of two high-speed cameras, one top view and one side view, and two microacoustic wave gauges. Using all this system, we could measure directly the overtopping flow depth and derive from it, and from the time passing from one sensor to another or during the frame of the cameras, we could derive the overtopping flow velocity. Just let's have a look at the result. First of all, we show the result in terms of average discharge and individual maximum volume. There is a clear trend. You can see, as we also know from literature, that for an increased discharge, we have an increase in the maximum volume. The largest scatter shown for the foreshore slope 1 on 15 is due to the kind of heavy braking that occurs very close to the dike, with an overtopping events that are very, splashing and very violent. And therefore also the randomness of this event is very, very high. Now, the trend that we saw before is not visible anymore when we look at the flow depth and flow velocities. Even though a certain relationship is still visible, maybe for flow depth versus the average discharge, anyway, we should admit that there is a large scatter. So actually a link is missing here, because meanwhile we could somehow relate the maximum volume and the overtopping discharge, we couldn't relate anymore the flow properties that characterize that individual overtopping volume to the overtopping discharge. So how we should behave with respect regarding to, let's say, the criteria proposed, for example, by EurOtop, that are just based on overtopping discharge and volume, if we lose this kind of relationship. Let's look again at the table from EurOtop and focus on the value of wave height of 1 meter, because it's the local wave height that we measure in our test upscale to prototype. So we have certain limits proposed by EurOtop in terms of discharges and in terms of volume. We then plot this limit on a graph together with our data. This is the first graph that I show you. What we can see here is actually that if one EurOtop criterion is fulfilled, the other maybe appears stronger. What I mean is that, meanwhile, for example, in terms of mean discharges, all the data are within, actually, the safety limit proposed for EurOtop. In terms of volume, most of the data, 90% of the data, are even above 1000 liters per second per meter, so far above the 600 liters per second per meter proposed by EurOtop as threshold for pedestrian. So let's try to look at the data in a different way. We can look at this slide and we have a graph at left that is very similar to the one on the right. It's just the way we plot the data, so we categorize the data that is different. On the left, the data are colored and plotted in function of the prominent or crest width and the range of overtopping discharge. On the right side, instead of overtopping discharge, we plot in function of the range of individual maximum volume. First, we can see that there is a large scatter independently on the measured discharge or measured volume. We cannot say that for a specific volume or a specific discharge, all the values are, let's say, in a safe region that is below the curves or in an unsafe region that is above the curve, actually. We should look more carefully at the crest width. And if we look carefully at the crest width, we can see, first of all, that longer crest makes that the points are moving towards the safe region. That is especially true for and evident for lower discharges, I mean less than 5 liters per second per meter, and for maximum volume smaller than 1000 liter per second liter per meter. That what does it mean? It means actually that there is an influence of the crest, an influence of the layout, that even if we consider similar events, even if we consider similar maximum volume and similar discharges, if we have a difference in the layout that generate a change, a transition, let's say, in the flow over the crest, so a change in the overtopping flow properties, perhaps we will have certain conditions that we can consider safe and other that we can consider actually unsafe. It's very important here the importance of the crest. Just consider that in our model the crest is horizontal, so it doesn't represent a change in the freeboard. Usually in prototype the crest has a certain slope, and longer the crest, the actual freeboard of the structure is even bigger. Fact that will somehow increase, let's say, the protection, increase the level of safety for that condition. So, if we have to conclude, first of all, we carried out experiment, and the experimental results suggest that further research is needed in terms of design criteria for wave overtopping if related to safety of people. Of course, we cannot generalize this work because we work on a specific layout of the Catalan coast, but it's already providing us certain indications, certain insight that on which we must work to generalize in future. We can also say that average discharge and individual overtopping volumes are still key parameters for the design of coastal defense, but it's our advice, or it's our, let's say, our work proves that the limit within the EurOtop manual should be at least updated, considering explicitly the velocity and the flow depth, and the velocity and the flow depth that are actually associated to the individual maximum overtopping volume. So the proposed tolerable discharge and volume values from EurOtop are still valid, but are not sufficient to identify clearly a safe or unsafe scenario. Finally, the overtopping flow, depth and velocity provide further insight, and are advised, both quantities are advised to be employed together and not alone, together with the EurOtop criteria for any coastal engineering design and coastal safety assessment. Thank you for your attention.